by Nico Bauer, Global Energy Sector Emission Reductions and Bioenergy Use, overview of the bioenergy demand phase of the EMF 33 model comparison. So over to you, Nico.
So thank you very much, Detlef. So Detlef is also part of this paper, so if you have terrible questions, ask him. And there's also a lot of other co-authors, because this is a model intercomparison exercise with 11 integrated assessment models. It is looking at the bioenergy demand part, not the bioenergy supply part. There's also an combining study on that, but I'm presenting the use of bioenergy here. And this is part of a special issue. This paper is now accepted by Climatic Change in the special issue, and there is also other thematic papers that dive more into details of technology and trade of bioenergy and other stuff. So you have certainly heard about the IPCC fifth assessment report and the importance of bioenergy for achieving the 2-degree target, and there's particularly BECCS that was based on IAM scenarios, partly derived in the EMF 27 exercise, and there were in the AR5 also lots of discussion about life cycle assessment, indirect land use change emissions, and so on. There came up a potential estimate of 100 to 300 exajoules of bioenergy production by 2050. It spelled out the different conditions to produce this. Post AR5, we have had a lot of commentaries on emission gap, moral hazard overshooting, target revision, and the production systems of bioenergy. There's also the discussions of alternatives, of CDR technologies, enhanced weathering, and so on. And we have the Paris Agreement and the 1.5-degree target, and the preparation now of the special report on the 1.5-degree target. The EMF 33 is about revisiting and revising the results of EMF 27 with a perspective on the bioenergy production and use. It is a more differentiated analysis, and we are working hard on relating differences in the scenarios to differences in models and assumptions. So the methodology is 11 models that are listed here, and a lot of very different characteristics and assumptions made in the models. I do not go through this. It's included in the paper. The important thing is all the models include, to some degree, where's the pointer? No, that is not the right one. Which one is? No, but now it's working. Okay, here, all the models except one, the Pulse model, have land explicitly represented at different levels of resolution. There's different ways of competing bioenergy with other purposes of land. The models are very different in that. The models have very different assumptions on the availability of advanced bioenergy technologies. I will come to that in detail later. And there is also the modeling of the entire energy sector in which the bioenergy plays a part. And this also explains some part of the results. We have a harmonized scenario protocol that was applied on all of these models. The carbon budgets are implemented by carbon pricing policies. The carbon budgets as such are harmonized, and they cover only energy and industry CO2 emissions. They account for CDR with BECCS, not the afforestation part. The other greenhouse gas emissions are priced on a CO2 equivalent basis. Also, the afforestation is incentivized by that. The carbon budgets are 1,600, 1,000, and 400 gigatons. They relate to temperature targets. And there's weak policies until 2020 assumed, and afterwards the models optimize and implement the carbon budgets. We have the advanced bioenergy technologies and biomass feedstock supplies, and we make variations. We have technology off scenarios, like no advanced bioenergy technologies, no BECCS, and no liquid fuels production from lignocellulosics biomass feedstocks. Then we also have a more gradual sensitivity. We double investment costs of the technologies, and we delay the availability until 2050. And we limit, finally, the biomass feedstock availability to 100 exajoule per year. So the net CO2 emissions and the bioenergy use, how do they look like? This is the baseline. You see with the emissions, there is quite some variation here. And these are the combined bioenergy uses in 2050, 2100. And you can also see here quite some variation up to 180 exajoules without any climate policy. The interesting thing is the low scenarios here are the high ones here. The high ones here are the low ones here. So less fossil fuel availability, scarce fossil fuel availability, leads to low CO2 emissions and high bioenergy use. When we switch on the different carbon budgets, we see that there is quite a funnel of the CO2 emissions. They all comply here with the 1,000 gigatons. And we see here also, again, very large variations. And again, we have a interrelationship. The high emissions here are interrelated with lower bioenergy deployment here, and also the lower emissions here are related to higher bioenergy use. So there's an inverse relationship here. In the end, when you have lots of negative emissions, you're also using a lot of biomass. Yeah? And what you also can see is we get here up to 400 exajoules. And most models show the pattern that they are sensitive across the carbon budgets in 2050, but they are hardly sensitive in 2100. So it's not about the final level, it is about when to start. Two models are showing the inverse pattern, less sensitivity in 2050, more sensitivity in 2100. And one model shows a, was ist denn? Shows here a decreasing behavior. This is a market size effect that is related to the aggregation of bioenergy into the energy sector. That's a tricky thing, has to do with economic modeling. You can say the harder it is to integrate bioenergy, the more dependent is the bioenergy deployment on the market size. And if you have to reduce fossil fuels, they draw down bioenergy as well. Yeah? Therefore, we have here this inverse sensitivity. What is the allocation of bioenergy use? So we have lots of models that do not assume, and this is the important part, biofuels with CCS. Yeah? So we see here a lot of green, and the models achieve very high levels also in the long run. Some models have bioliquids without CCS. And they are these models are going very much into the electricity with CCS direction. However, the BECCS technologies also produce energy, and other models also assume the biofuels with CCS, and they go a very different route. They are applying much more of the bioenergy, the biomass, to this conversion route. Biofuels with CCS. Not so much the electricity with CCS. And what you also can see is models that have quite a high deployment in the baseline. They upgrade the bioliquid plants in this scenarios with climate policy with a CCS. So this is the extra effort required to make BECCS happen. What you also can see is BECCS is very important in the use of bioenergy, so the share of bioenergy equipped with CCS is very high. And yeah, now what we do is we switch off some technologies and look what is happening to the total use of bioenergy. And we see here a table, the high and the low budget case, no advanced bioenergy technologies, no BECCS, no liquid fuels technologies assumed, 2050 and 2100. And here's different classes, and they say how much of the bioenergy that would potentially be reduced by banning the technologies is used for other purposes. It's a kind of a rebound effect, you can imagine. And it's the biomass supplies that become idle, they find new and alternative demands. They're used for different purposes. And with the same carbon price, fossil fuels would increase again. Therefore, we have to increase the carbon price. And this reinforces the reallocation effect. And then with the stronger climate policies, we have a feedback again on the bioenergy demand. And this can lead here to various models to use 50 to 100% of the bioenergy for different purposes without, for example, CCS or non-liquid fuel production. And so here 10 models are in the 50 to 100% region. And in some cases, it can even be more, because the CO2 price increases, and then you need to use more bioenergy rather than less, because fossil fuels are need to be reduced. When we now limit bioenergy use to 100 exajoule per year, you see something similar. This is now the gigatons of CO2 per year removed from the atmosphere by BECCS. And this is with a full portfolio, and this is with a limited biomass constraint. And you see some models use or deploy more carbon dioxide removal, because you also have a higher CO2 price, and this leads to this kind of inverse sensitivity. And it's quite some models that do this. By 2050, 2100 it is different, and what we see is we do more CDR, more carbon dioxide removal with less bioenergy. The models are so flexible to reallocate the use of bioenergy in such a way. Now the carbon price sensitivity. This is a present value price. We map we project the carbon price trajectory back to today's levels to make them comparable across time and across models. And here you have some additional interesting information about the levels that you see here. And with a high budget, CO2 prices are low. The variation across models is not that large. With a low budget, the variation gets larger. We have here an outlier. And when you go to the very low budget, CO2 prices have to be very high, and the range across models increases very much. Now, if we limit biomass, assume no BECCS, or ban advanced bioenergy technologies altogether, then we get increases, percentage increases over these levels. And you can see limiting biomass has quite a profound effect on the CO2 prices. So this is doubling, tripling. But having no BECCS at all is worse for all models. This is a consistent pattern. The price increases is worse. And when we look for more gradual sensitivities, so not the complete on-off thing, we see, and this is very interesting, so this is doubling of investment costs, and the CO2 price increase is less than 25% across all the models. And it does not depend very much on the budget that is assumed. However, if we delay the availability of all the advanced bioenergy technologies, then with the low and the very low budget, the price markup is much higher because their usually models start earlier. And if you delay until 2050, then this becomes more serious. So, conclusions. We have differences in results, and they are related to differences in models. This is in the paper, it is much more detailed, going into single models and getting that out. The important thing, it depends on feedstock availability, bioenergy technology availability, it's the potentials and flexibility of all the alternative decarbonization options, it's the fossil fuel abundance, and the emission profile over time to allocate the budget. Lowering fossil fuel use drives bioenergy use in the baseline, across the models, but also across the budget cases. And what we see is stronger carbon budgets imply higher bioenergy deployment. And we reinforce the finding of the AR5 report that advanced bioenergy technologies are crucial for decarbonization. However, bioenergy is flexible in use, and the allocation depends on the energy as well as the carbon value. So the liquids are more valuable than the electricity. Limiting the advanced bioenergy technologies leads to reallocation and this policy feedback effect. And, but what should also be emphasized, bioenergy in the overall mix is limited because 400 exajoule is way below what we are currently consuming. And the energy demand is going to increase, so there must be also other solutions to supply clean energy. So thank you very much for your attention.
Thank you.